All right, so a while ago I made this game called Louie, and it has a map editor, and I made it in Unity, and I thought it would be fun to go over some of the what I think are like the cool tidbits from the map editor. So see how far we can get, but I wanted to talk about like how objects are represented in the map editor. I wanted to talk about how I handled serialization. There's like some scripting stuff that we can talk about. I'm fascinated by the tile map in Louie, so I want to talk about that. Navigation and pathfinding. There's some procedural generation stuff I want to go over, and then some like if we get there, I have some self-proclaimed wise words. So my big disclaimer is that through this process, I learned that Unity is very flexible and powerful and should be respected. And if you try to disrespect Unity, it's not going to work. So one of my mantras for this project was to try and do it the Unity way as much as possible and to not reinvent the wheel, which was really hard for me personally. I wanted to like do everything by hand. So diving right in then. Louie is a 2D platformer. This is what it looks like. This is the map editor itself. That's about all the intro to the game I'm going to do. Louie is a game about walking through a door, and you need to walk through lots of doors in the game to win. So I figured doors would be a good place to start talking about objects. So this door, what is this door? In answering that question, it's useful to know what doors can be and what make them unique. Like, so doors can be either open or unlocked. They can have an X offset, so it's kind of hard to see, but like this blue door versus this red door, one's kind of at the edge of the wall and the other's in the center. So it's like an X offset. They can be colored, so these are all different colors, and they can have rotation. So they can have like trap doors if you wanted to. So really, at the end of the day, it's the properties of the door that make them unique, and that's what we're going to dive into next. So the door itself is just a prefab in Unity, and when you're using it in the level editor, all these different properties show up. So actually, that door is, yeah, like I said, a prefab. It's a game object, and it has a gazillion components. The ones that I want to focus on right now, though, are these things in the flavor of arg something behavior. I don't know if you can see the small text here, but it's like arg bool behavior, so on and so forth. So each one of these maps to one of these properties in the actual level editor. So when you're like editing data in the level editor, you're actually talking directly to a component on a game object. So these arg behaviors come in two major flavors, I'd say. They all have a name and a value. And then depending on what type of flavor you're in, they either have some sort of range, like a min and a max and an increment. So that's something like health or the offset or ammo, or they could be kind of a set or a collection. So again, they have a name and a value, but instead of a range, they just have a set of possible things. So a Boolean is a good example. It's either true or false. And so let's see, as you change these properties, can see that the actual value in the arg behavior changes, which drives some sort of behavior in the actual game object. So as I'm clicking around offset, this door is sliding left and right. And the code that actually handles that isn't super interesting, but I just wanted to call it out that these arguments can be accessed from other parts of your code base. So like there's the whole door behavior on its own that has a reference to one of these arguments. And in its update loop, it's just checking if the argument is dirty. And if it is, it resets the local position based on the value of the offset. So the reason I included this code is just to illustrate that, like, cool. So the user can edit these properties. These properties get stored in components, and now some other script can act on that that value. And yeah, I guess I'll dive into the arg behavior a little bit more. They all have these functions: next, previous, get, object, and set, and these roughly map out to like make the value the next thing possible in a ranged argument. That would just be like increment the value by some set increment. Previous does the opposite. Get and set, pretty self-explanatory. But from that come a pretty rich type hierarchy of arguments. And And I'm not going to dive into all of these, but just by way of saying, there are lots of these. There are even more that I didn't decide to put on the slide. And that supports lots of customization. So it turns out that really all these doors are the same prefab with different values in a couple of key critical properties. And then, needless to say, all of the other game objects in the world, like a key or a spike or a bad guy, they have their own sets of properties that adjust how they look and behave. And so really, like, all of the objects in the map editor, they're just prefabs with these property components layered onto them. And that's, I think, big takeaway point number one. And you may say, this feels way too complicated. You might know how to code and you think you should just use a class variable to represent this stuff. No, you should not do that. Well, you could, but if you do, then you won't be able to test your code as easily. It's harder to write shared editors. With this like component as data sort of thing, you can expose pretty complex operations like what kind of hat do you want to be wearing? You get to reuse a lot of behavior code. So like the way that health works in Louie is that there's a component that watches an int argument, and when that int argument goes to 0, it destroys the target component. So that's a way that I can now share that across a ton of different game objects, and it's just operating on data as a component. So that's really cool. Two other things we're going to talk about is using this argument stuff as a baseline. You can implement a scripting system pretty easily, and it's actually now pretty straightforward to serialize these objects because the only thing that you need to serialize on the entire instance are the property values. Because, like I said, that's what actually makes them unique. And I mean, you could do all that if they were class variables, but I think it would be harder. So before I that's it for like properties and game objects. Next up is serialization, but I want to pause and ask if anyone has any questions about that general approach.
So I was wondering why multiple components and not like a component that could have an array of widgets on it. Is it the flexibility, like having it granular with a lot of things? Does that make it easier in some way?
That's what I found. Yeah, exactly. If you have a character who has ammo and health, and having those as two separate components makes it easier to reference them. Because you can, like, Unity acts as a dependency injection engine, like you drag and drop references around. And so if you need to reference the int arg, it's really easy to do that when the int arg is a separate component entirely. I don't have to build any sort of extra addressing system on top of the fact that it's a component. Does that make sense?
Yep.
Or does it answer the question?
It does answer the question. Yeah.
Yeah. Cool. Then moving on to serialization. So how do we serialize this stuff? Here's a bunch of JSON. It's a lot. Actually, this is just the JSON for one single door. So when you save a level, you get all this JSON just for that one object, which may lead you to say, level must be huge. The levels JSON, I checked, they range anywhere from 100 kilobytes to 250, which I get is a lot of JSON, but really in the grand scheme of modern day computing is not unreasonable. So a level is a ton of JSON pretty much just crammed together. It's worth noting that actually the game has 25 levels built into it, or 26 or whatever. The JSON is actually baked as a scriptable object when I ship the game so that people can't muck with it. Like, you can't open up the game files and change the JSON, but as an intermediary stage, it was represented as JSON. And for me, this is really helpful because if I'm having some sort of issue with my level loading process or something's weird, I find it way easier to debug JSON and just open up the data than any other format I've come across. But that's definitely a personal preference. So anywho, how do we actually get to that JSON? Well, I have a component called a save behavior. And really important, it has this layer code. It's just some string, but it has to be unique across every type of thing you'd want to save ever. And then it has a list of components that you actually care about. So this save behavior like lives on the door game object, and I'm saying I care about my transform, and then mostly all these arg behaviors. And there's a couple other ones scattered in there, but they're not worth talking about. So these are the components that I want to save when a save needs to happen. So yeah, these are just referencing components on the door itself. Inside of that component, there's a function called save component that takes in as some parameter whatever component we happen to be talking about. And it's going to transform it into something that isn't actually quite JSON yet, but it is something that will be very easy to transform into JSON with something like a Newtonsoft library. I'm not sure if people have tried to just use Newtonsoft to serialize a mono behavior before, but it's a bad idea because you get a bunch of extra cruft that you don't want. So that's why this step is important. Is we don't actually want to be serializing mono behaviors directly. We want to be just the data we care about. So here's that code. It's really gross. Here's that code, less gross. I commented out a bunch of stuff. Really what it's doing is it's a giant switch statement. It's not very efficient, but different types of components are best suited with different types of serialization. So like the transform serializer only needs to serialize a couple key pieces of information. Whereas if you like this big else case at the bottom, this is like a big scary one because we need to map over the component and like just kind of find the fields that we think are valuable. But if we know that it was a transform, then it's way easier to write the serializer for that, and we do, and it makes it faster. And that's really how it gets saved. I'm jumping over a lot of stuff, but ideally, the really critical part is that you mark the components you actually care about, and during a save event, it dumps out to these different types of serializers and yields you a ton of JSON, and that just gets shoved into a file. And that is the level file. Which leads to how do we load that data? Remember this layer code property that was on each save behavior? Well, that comes back to play. We pretty much say in the scene, we're going to have a bunch of object loader components. It doesn't really matter where they're kept, but there needs to be at least one per layer code, and it references some prefab. So pretty much you say, when you're scanning your JSON and you come across an object that's marked with the layer code of doors, then you spawn up this prefab and you apply into it all of the properties that were serialized. And that's how stuff gets loaded. So that's it. I know I'm kind of moving fast over that, but does it generally make sense to people? And are there questions on that?
I have a couple of questions.
Yeah, shoot.
You mentioned that the else if stuff was not very efficient. Do you mean that it compiles to a costly bytecode, or just that it's not efficient in terms of lines of code?
Oh, I just meant in general, this type check kind of style. I generally don't like doing it, but I always find myself doing it anyway. I guess it's not efficient in the sense that the serializer that will be used in the else block, like the catch-all general serializer, that is not efficient, really.
Okay.
It's using reflection to actually look at the public fields on whatever game object you give it, and it's turning that into key value pairs. So actually, I can go back a little bit and say, in this JSON, one of these objects, like this block here, this is actually that's a bad example. A better example is, in the top left, the transform. So it's saying there's an array of components. This first one was serialized with the transform IO, and then it has some general component data, and this is pretty well defined. But something that was serialized with the general IO has an array of fields, which are name and values. So the general purpose one is less efficient. That's all I was saying.
Okay, and so the saving and loading code kind of tries to apply this using reflection to stuff.
Yeah. Yep. So it's definitely a case of.
Oh, sorry.
Oh, go ahead.
I was gonna say, is the idea here that you just didn't want to write the serializers for all these other classes?
Oh yeah, hell yeah! I was lazy.
Yeah, got it. Okay.
So I could have written serializers for each specific one. Like there's a good example here. It kind of wraps onto the next one that has its arranged arg called rotation. It would have been pretty straightforward to write a custom serializer for that because you only ever need those 5 values: min, max, increment, value, and name.
Right.
I just never got around to it. So
yeah, which is fine. I was mostly just curious if there was something special about these particular components that made it especially difficult, or if it was just a choice.
I'd say the one thing, like for transform, if you pump transform into the general IO thing, you're going to scrape a lot more data than I actually want. Like there's more fields on transform than I want to actually be serializing. So there were some that necessitated a custom serializer like transform.
Yeah, that makes sense.
So the other question I had was the layer tag. It looks like that it's a 1-to-1 prefab to layer code thing. So only doors belong on the doors layer, only spikes belong on the spikes layer, so on and so forth.
Correct. Yep.
Now, Unity itself has a layering system for its UI. Is there a reason you didn't use that, or is that not basically not doing the same thing?
I didn't want to repurpose the UI layering system, so I used that system, but I didn't want to like the serialization layers are kind of orthogonal to the layers in the UI, and if I tried to use them for both, I would have run into like, oh crap, I need this layer to be one thing in the UI, but I need it to be a different thing in the serialization, and I wanted to not have that problem.
Yep. Okay.
Cool. Data gets loaded. Okay, so moving on. The next thing I wanted to talk about was how do doors open. Continuing with doors, but this is going to lead us into the scripting system. So I use this word called signals and actions. So when you click on an object in a particular way, you open up its like scriptable options. Actions are things that the object can do, and signals are things that the object can broadcast. So just to really drive this home, in this case, the turn on action is like literally flip this switch on. And the on signal is literally just like, hey world, I'm on. So did we just lose someone or gain someone?
Brandon is here now.
Yeah, just
hello. Yeah, so yeah, actions do things, signals broadcast things. And these are only ever Boolean values. So you can't like pack arguments onto these things. They're literally just like yes or no's. You click on the door, you say I want its on signal, then you click on I'm sorry, I said that wrong, but the signals of one object will drive the actions of another object. So in this case, the on signal from the switch will trigger the door to open. And again, yeah, so diving into that a little bit more, these are all backed by components, and these are actually subclasses of that general arg component from the beginning. So in the case on the left, the actions are these things called signal name args. The name is kind of misleading. I wish I had called these like action args, but I didn't. So this switch game object actually has 2 components of this type, one with a name of turn on and one with a name of turn off. On the right side, there's a signal behavior component that drive the things that can broadcast. So there's literally 2 components on the switch, one with on and one with off. So I'm going to dive into what those actually look like next. So the signal behavior itself needs a couple of things. It needs a name, like I said, these are all just Boolean values. So like, is the signal on or off is what the value is. Then ID is a unique GUID string. Once this signal gets created, like once you create the door in the world, it will give itself a random ID, and then that random ID is never going to change. Like it gets serialized with the data. And so, yeah, the serialized form of this is just like, there's the name, there's the value, there's the ID. On the other side, the signal name, which again, kind of misnomer, this is the action itself. This has a display name, which is open, and then it has two fields which are a little bit duplicitous. Like they're kind of representing the same thing. It's the display name of the signal that you're hooked up to and the ID of the signal that the action is hooked up to. So in this first one, up here in this little image, the switch is not connected to the door yet. But if you connect them and you get this orange line telling you that they're connected, then the signal ID is going to map to the same GUID on the door's on signal. And so that also gets serialized as this. So with some data, we're really just stitching stuff together. And that's it. That's how the actions and signals like get connected. And then there's code out there in the world that turns them on and off. So I have this component that I use all over the place called a receiver behavior. And you give it some action that you're watching for. You give it a bunch of functions in the activate and deactivate thing. And so like the activate ones are literally just do these things when the action starts equaling true, in this case. And the deactivator is the opposite, just like run these functions when this signal is no longer true. So in this case, it's literally when the open door signal is true, go and run the open command on the door. So between the signal name arg, the signal behavior, and the receiver behavior, that's really how all the scripting is done. There are lots of things that can be scripted. So here are a bunch of the buttons, components in the game. You can see they each have lots of actions and signals. And then there are like Boolean operators that you can use, and you can stitch these together to make some pretty cool in editor interactions. So yeah, if not actually going to like explain what the hell each of these screenshots actually looks like in game, but I assure you that interesting things happen if your character goes through these areas. And yeah, I wish I had more effort to make the lines not look like garbage, but it was not worth the time. And that's scripting. Are there any questions about how that works? Cool.
Yeah. One little question.
All right.
Sure. The GUIDs, do you just generate those as soon as the door is created or whatever object it is? Or are those pulling from like game object IDs in Unity?
Yeah, they just get created as soon as the object is created, and they're created randomly. So when you actually place a door in the scene, it goes through the on awake function on the signal behavior actually just says like, hey, if I don't have an ID, just give myself an ID, and it's random.
Cool.
All right, so let's see. Cool. Cruising through this, so plenty of time. The tile map in Louie, I think this is fascinating. This is like my head exploded when I figured this stuff out, so I want to share it with you guys. Here's some tiles. How are these tiles represented? With a grid. So at this resolution, this is the data that's actually like stored to disk. Because like you can't have any tile smaller than this in Louie. But actually at the art scale, all the tiles are much smaller. So you like shrink it by a factor of 2. There's a really good reason for this that I'm going to get into. So each full-size tile is actually 4 little art tiles. So here's this little grid, and in memory, when the game is running, it's like deserialized the level from a file, and it actually assigns the grid just a whole bunch of ones and zeros. So in data, it really looks like this. And under the hood, this is one just big giant array of ones and zeros. So now we've got this kind of setup, and we need to figure out how to actually render like the art itself, because I kind of did this in reverse, but really we have ones and zeros, and now we need to come up with art to render on top of those ones and zeros to make it look nice. So the question now is, like, if we're on this tile here, what art tile should we use? And I have this crazy component that defines these rules that say, based on your 8 neighbors, use some particular tile. So in this case, because there is a neighbor down from this tile, and there's a neighbor left from this tile, but not one up or right, and the use corner is not checked, then I can use this top right edge tile. And so there are quite a few of these rules. There's 13, in fact, and they map to these 13 tiles, which is not really important, but they're sourced from this one image. And yeah, that's how that works. I think it's pretty straightforward. If you guys have used the tile editors in Unity before, you'd be like, hey, wait a minute, Unity already has a way to do that at edit time. But I could not for the life of me find a way to replicate it at runtime. And in addition, it seemed like if you were going to use Unity's built-in tools, you would have needed to come up with like a bajillion more art assets. Because the approach that I'm using strictly requires 13 to fully capture like every wacko combination set of tiles you could come up with, which is, I think, it's mathematically super cool, because if you didn't do it that way and you actually were going to render the art at the same resolution as the data store, like at this resolution, and so you need a tile to represent, like, oh, what if there's like one tile below me but no tiles on the other sides? Then how do you represent that? And counting that up, you may guess, is going to go crazy. So if you just kind of think through it, and you are looking for all of the variants where you only have one neighbor, that's the same as 8 choose 1, which is 8. And then if you start counting, like, well, now what if you have 2 neighbors? Like, what kind of art should you render there? It's quickly going to become apparent this number is going to be huge, and it's actually hard to count. So using some math, you can actually just sum up, like, well, you have 8 options, choose one of them, that's your neighbor. You have 8 options, choose 2 of them, that are your neighbor, so on and so forth, until you get, like, you're completely surrounded. And so these are the possible values, and that actually maps to, in order to capture this, you need 255 art assets, which,
hey, that's coincidentally 2 to the 8th
crazy.
minus 1.
Yeah, because I did not include 8 choose 0, so it doesn't go to 256. So, like, I'm positive that other game developers who have made 2D tile maps have not had to create 256 art assets. I just could not for the life of me figure out how you would avoid it if you didn't lower the resolution of your art assets. So yeah, this is like fundamentally cool to me. I don't really even know how to put in words how cool it is, but I think it's really neat that when you take your grid size and multiply it by 2, you can get away with representing the entire set with only 13 tiles instead of 255. Yeah, and then worth in calling out, this tile set is actually 2 separate tile sets. There's one for the fill, and there's one for like the perspective border around it. So technically I need 26, but whatever. Yeah, and that's tiles. This is more for me. I think this is fascinating. Does it make sense, like the math check out to people?
Yep.
Cool.
Yeah, this is really neat. Actually, in the tutorial I was going through in Godot, they actually have a tile set tool that's super neat, and actually is essentially doing this as well. Basically, what you do is you set up your tile set in a way that you can subdivide each individual tile into a 3x3 little block, and you set it up as a tile mask, and you basically select where in basically what you did here with, you know, the upper left, upper right, top, etc. And you can basically like visually say this one is going to represent when it's touching these other ones, and you just basically fill out the whole thing. And so it seems to be essentially the same math, which is really neat. But yeah, it's really cool.
Yeah,
Justin,
cool
could
stuff.
you toss a link to that Godot thing in the channel somewhere?
Yeah, absolutely.
Yeah, I know Unity has a similar thing too, but it seemed like it only worked at edit time. It was like an edit time thing that it was doing. Anywho, moving boldly ahead to the next thing is pathfinding. So there's this little robot guy who will chase Louie around in some of the levels, and he's a total jerk, so you have to escape him. So how does this work? Pathfinding in the abstract, if you had a graph, which is just a bunch of nodes and edges, where the nodes are the walkable spots and the edges are the possible motions between those spots, then you could use any kind of pathfinding algorithm you would like. I used one called A*, and then that would generate you a set of edges, and you just have to move the character along those edges. So that's like where we're going. But now, in detail, the first step is to generate the graph, and that's in a couple of different steps. So we need to come up with the nodes themselves. So we're just going to focus in here, and remember, this is just a grid full of ones and zeros. So coming up with the walkable spots is really just this little pattern match of like you're checking a cell, it has to be empty, and the cell below it should be non-empty. It's really that's it. Then that spot is walkable. And just repeat that for every cell. And you wind up getting all these little circles that represent the nodes in the nav graph. And then I store these nodes, I think primarily in a hash set, but in different structures for different sorts of access patterns. Cool. So the next one is we need to come up with like the walking edges. Like how do we walk between nodes? And again, let's just focus in on this one little section. These three dots represent positions and nodes, and those nodes have coordinates. So this coordinate is like, it's not really, but let's pretend it's 0, 0, and 1, 0, and 2, 0. This is X and a Y. Then for every single one of these, we're just going to say, hey, can I go right? And that's the same question as asking, is there a neighbor immediately to my right? And if there is, then I'm going to say I can walk to it. And if there's not, then I can't walk to it. And that's pretty easy to do because we have a hash set. So we can really just say like, hey, does this exist in the hash set? And if so, great. There's a little hiccup here with doors, which I'll get to later. So really that produces, connects these things, and you run it for every node, and voila. Now all of your nodes are connected with walk edges where it makes sense. The next one is jump edges, which is much scarier. Oh, right. Forgot the order of my slides. Moving too fast. I actually decided to represent the graph like this, which is kind of odd. I had never written a graph like this before, but I have a bunch of nav target sets. And you can think of it, the origin is where you start in some particular place. And then you have a dictionary that goes from destination to ways that you could get to that destination. So it's kind of an odd representation, but it worked really well for this use case. Right. So jump edges themselves, focus in on this section. And remember, these are all just coordinates. So we're just checking, like, how do we connect these abstract coordinates together? And the answer is to pick one and simulate a jump with some velocity. So the code that generates this nav mesh actually, like for every node, just tries and says like, okay, what if I jump this way? Am I colliding with the tile map or anything else that would stop the jump? Or did I hit another node successfully? And it tries it and it sees that, oh, it can get to 0, 0. So it remembers that edge with that jump velocity. And it tries another one, and it tries another one, and it tries another one. And eventually it will hit one that doesn't work. And so it discards that jump velocity. And then it goes back to trying some other ones. And in fact, it tries quite a few. So every single freaking node will run through all of these initial jump velocities. It's quite a bit of computation, but we only need to generate this nav mesh once when the level loads up, so it's not so bad. Yeah, there's a little hiccup though, where if you find out from this node here and you're jumping up and to the left and you like see that you are close enough to this node to consider that, like, yes, I can get from that node to this node, it's super likely that actually the jump velocity is going to lead you close to that node, but it's not going to lead you exactly to the node, which is actually a huge problem when we get to the next step about how we follow the motion paths. So there's a little bit of shenanigans here where once you know that two nodes are jumpable, you can back solve for the exact velocity that would lead you between the start node to the destination node, so that like when the jump is done, the character is standing exactly on that node, which comes in super handy in a second. Right, and so you do that for every single node, and you get something that looks like this, which are, we now have all of our edges. So pathfinding in the abstract would mean that now it's time to do an A* search. So we're going to go from one spot to another spot. And I'm actually not going to talk about that. It's pretty well covered in a lot of stuff on the internet. So I would reach out to Wikipedia for how to do A* over a graph. But let's assume that you do have a path and it looks like this. How do you move the character along the path? I think is a more interesting question. And that comes down to how I represented the edge class in code. And I want to call attention to this interpolate function. So every edge has this magic function that when you give it a number from 0 to 1, it's going to return you a position in the world, such that when you give it 0, the position will be on the start of the edge. When you give it 1, the position's at the end of the edge. And every value in between is going to move some objects smoothly along that edge. So if every edge has such a thing, and we can take a look at like all of the walk edges implement that function with a pretty standard linear interpolation function, and all of the jump edges implement it with some projectile physics, which again, this pretty much comes from Wikipedia for how to simulate this kind of stuff in constant time. Like it's not doing like a simulation, it's just doing the math out. Once you have such a thing, there's a component called a path follower that takes in some transform that it's going to move around the world. And in its update loop, it has a current edge, and it pretty much just sets the controls position to that current edge interpolate. So it's going to just move the object along the edge, and when the interpolation value gets above 1, it'll go off and prepare the next edge. The reason that's baked into a separate function is 1, for just like code cleanliness in a presentation, and 2, there are a couple of odd little hiccups to check if the path is like done, like if you're at the last edge, what it should do. But yeah, and now the result of this is that you just have some transform moving smoothly along the path, and then there's a whole separate unanswered question about how do you apply animation to that, but I'm not going to dive into that today. And I mentioned that there's a little hiccup with doors, so if you slam the door in the robot's face, he will automatically path around it. And the way that that's handled is that anytime you close a door, you just find the edge that that door goes through, and you set its edge weight to like infinity in the A* stuff, which effectively means the edge is not traversable, so the algorithm will never pick it. And yeah, that's pathfinding in Louie. Moving platforms, teleporters, and lava are just not implemented. So like bad guys cannot use moving platforms or teleporters. And if they want to, they will just jump on lava directly, which usually doesn't happen in the game. But Yeah.
This means that they don't actually, they're not attached to the physics engine at all, right? They are just following the paths. They're just interpolating along the paths that were calculated. Is that right?
That's 100% right.
Okay.
There are a couple of weird times in the game that the characters do need to be on physics. So like that little robot, if you shoot him, he'll fall over. And if you shoot him on a cliff, then he'll fall down the cliff, like because physics would say that something in midair should fall.
Right.
So like, yeah, the character controller, when they're just moving around, takes them out of the physics loop and then decides to put them back into the physics loop when it makes sense. But yep.
So, very interesting. Okay. Huh.
Right. Are there any questions about the pathfinding stuff?
Yeah, you mentioned edge weight. Did you assign different weights to like the walking edges versus the jumping edges?
I did. Yep. So it's jumping edges always have a higher edge weight than walking. So if it can get there by walking, it will. You can even see in this GIF though, there's a bug where for whatever reason, sometimes they just jump randomly. And honestly, I never figured out why, but he'll do it like right there and he'll do it right now. It's like a stupid little jump to the edge. So the weight is a mixture of what type it is and also the length, like the physical length of the edge. So if you have a jump that's really long, that will lead to a higher edge weight than something that's really short.
It may just be that that jump was the most efficient way to get there, even though it was long.
Maybe, yeah. I mean, that would make sense. I don't know how that
like
could be.
4 or 5 walking edges, right?
Yeah, it definitely might be that. I remember seeing it and being like, ugh, I should fix this. And then I never did.
It makes the robot
right.
a little weird, which is fun.
Yeah.
The other question I had was, what's the thing? Question about. Oh, pre-baking the nav mesh. You said you do that when the level loads. Would it be possible to even do it earlier than that? Or is it fast enough that...
I definitely thought about that. Yeah. So I lied a little bit. It does it when the level loads, but it also does it on a couple of critical moments in the game. So there's
Like
nothing in this presentation to say it, but if there's secrets that in the game that you can open, and the nav mesh will respect those secrets. So it's literally like a wall that vanishes when the secret has been revealed. So the nav mesh has to regenerate anyway during the level. That's why I decided not to pre-bake it, is because I was worried that if I let myself pre-bake it, then I would make it too slow. And if I force myself to make it have to run like in the actual game loop, then it would not be so bad. So diving a tiny bit more into that, it actually, the way that it works is it's a progressive algorithm. So it starts generating it in a coroutine. And when the entire coroutine has finished, then it actually swatches over the nav mesh. So there's actually a bug in the game that you can get to happen if you try really hard, where if a bad guy is chasing you like into a secret and you open the secret and run into the secret area, the bad guy won't understand that it can get in there until the nav mesh actually rebakes. And so it'll just kind of like stand stupidly outside the secret. But it definitely is a small enough gameplay thing that it's just how it works.
Chris, I have a question. Why is the A-star algorithm like the most common pathfinding algorithm in games?
It's kind of like the grandparent of a lot of pathing algorithms. It's really easy to express. Like if you look it up on Wikipedia, it can be implemented in like 12 lines of code. So it's really easy to think about at that point. And then there are a bajillion variations and optimizations that can be made on top of it. And I would actually say likely in AAA titles, they're not using like Wikipedia off the shelf A-star. They probably have some super highly optimized variant of it.
Having
because it's
implemented
so-
one of those, I
yeah.
can tell you that is 100% true. Actually, StarCraft uses a variant called triangulated A star, which it's almost pretty much A star in name only. I mean, there are similarities to it, but you can get really fancy with some of the geometry and how you parcel out the level. That is, you parcel it out as triangles or as a grid or and so forth and so on. Whether you make it deterministic or not. So all of those things, but it's a great place to start. It's a great foundation, and there's a bajillion implementations out there. So if you're getting started in pathfinding, it's a great place to start in general.
Yep. Cool. All right. Yep, they're not implemented because I didn't have time. Okay, so the last thing I wanted to, or one of the last things, I just wanted to really spin through some of the procedural generative stuff. I picked two of my favorite examples. The first one is the sky in the background. That's all proc gen stuff. And then the second one is the level, the island itself, and the level selection area. Like the character walks around this island and picks levels, kind of like a overworld. Anywho, diving into the sky, I'm going to zing through these slides, and if people are interested, I will happily go into detail. But so for a cloud, you start by rendering your UV or GV space, and then from that, render a circle. In the shader presentation from a couple months back, there's a little explanation for how to do this. Once you can render one circle, you can render 3 circles just by offsetting your original, like where are you drawing it spot. And your centers are actually going to be radially from 0 degrees to pi degrees around the center. So in this case, we're only rendering 2 extra circles. But if you decide to render 5 extra circles, then you just pack them in like this. And already this looks like a cloud. So that's cool. Just by rendering circles. But if we keep on going, you can come up with a mask full of 1s at the top and 0s at the bottom of the image and multiply that over the cloud, which cuts off the bottom, which makes it look more like a cloud in my opinion. And then it's always wise to blur the edges if you can, because it will help reduce artifacts down the road, and you can reuse it for outlines, which we will. Then there's this crazy step that is pretty common in ProcGen frag shaders, where you can take your original GV space, and instead of just having one of them, you multiply and fold the space as many times as you want. And so now there are tons of clouds, but this looks too much like a pattern. So just randomly don't draw some of them, and then offset them vertically a little bit, and then offset them horizontally a little bit. And now all of a sudden, this starts to look like a sky with random drifting clouds. The next step is, instead of drawing all of the circles exactly at like evenly spaced from 0 to pi, like mess with them a little bit, like change the radius, change the angle. And now the clouds have a little bit of variation, which is nice. Throw in some color and use that blurred edge to allow yourself a outline, and then repeat that process a couple of times. And every time you repeat the whole thing, just like make your space bigger so the clouds get bigger, and then make it move. Just kind of animate your UV space on the X, and now you've got these nice scrolling clouds. So all of that, there's a little shader toy link here. It's really gross, but if you're curious, you could go look. And in Unity, I added a gradient background and some stars that show up behind the clouds, and a little bit of normal mapping on the clouds themselves, which I'm not going to go into now, but it's kind of hard to see. But in some of these lighting scenarios, you can see that the left side is a different color than the right side on the cloud. Yeah, and that's clouds. That's how those work. I just think it's cool that they start from nothing and wind up looking like this. Yep, cool. So if there are no questions on that, then I will just zoom ahead to the next one, which is the island.
I have a question. That
Go
normal
ahead.
mapping, is that also procedurally generated, or is that defined?
It is.
Cloud? Okay, interesting.
I probably should have put a slide in about it. When every circle, like when all of the circles are getting generated, it doesn't just generate the circle, it also generates a normal map for that circle in particular. And anytime that the circles overlap, it just, I think it just takes the next circle. So it blends them together based on the radius from each circle. So like where the highlighter is right now, actually right now, that would get a normal affected from 2 circles. And so it just averages them based on the percentage radius from the center of each one.
Okay.
And when I say normal map is being generated, it's literally just like if it was we're generating the spot where the red dot is now, it's just the vector away from the center of the circle would be the normal vector on the cloud.
Right. And you're doing that specifically such that they can be uniformly in the same direction, right? So that would apply the shading. It's basically showing that there is a single light source in the scene, right? Like it seems like they're all the same in that picture.
Yep.
Okay.
Yeah, they are.
Cool.
Cool. All right, so the island, this is only half procedurally generated because I start out with a like island PNG image file. So that's what this crazy thing on the right is. This red yellow amalgamation is actually the input texture for the island. So working through this, take that image and treat it as a height map, where the brighter the pixel, the higher that part of the land is. And then band the height map. So in this case, like some threshold has been decided such that green is land and red is not land. And then band it again so that you have green is land, red is some sort of shore, and blue is water. And we're going to discard the blue because it's just like we're going to inherit the background from the whole scene. So the blue goes away. And also, instead of using like solid fill colors, pick some nicer colors, and maybe those are textures that we layer on top. So with those steps, we get something that kind of looks like an island. The next big thing that we want to do is get the waves that kind of come in on the edge of the shoreline. And so the first step there is produce this sort of wobbly animation and use it to displace our height map. So if we displace our original height map by this one, then the shoreline wobbles all over the place. So this is at 12 speed, so it's pretty, I tried to make it easy to see. Hopefully it's showing up over Discord, but the edges are going crazy. At regular speed, it's really hard to see, but if you like focus on one spot, you might see it shift ever so slightly. So it gives us some amount of like wave kind of atmosphere. And then the next one are like the froth lines. So like there's some like waves crashing on the shorelines themselves. So to get that, go back to the height map, and there's this magical property in Shaderland called frac or fractional, and it takes the fractional part of any input. So if you gave it like 1.2, you would get 0.2 out. It just discards the whole number part. And so if you take the fractional part of the height map, you get this image. And what's cool is if you take the fractional part of the height map times 2, you get this image, which starts to look pretty trippy. And I'm going to zoom through these. If you multiply it by something bigger than 2, like 20, then you get this crazy thing. And instead of just multiplying it by a number, if you also subtract or add a number, and if that number was animated with time, then you get this totally trippy, like transcendental thing. But this kind of looks like waves, and if we multiply a mask over it, it looks more like some crashing waves, and now we can multiply that on top of where we were before, and around the edges we get this kind of like, it's not perfect but close enough sort of wave pattern that shows up. Yeah, and then we also, the last thing we need to do is have paths. So that was the green channel in the original source image. Just multiply that on top of a path texture, and then add that back on, and that is the island. Which is kind of fun. So you can, I had fun like in paint.net just changing the shape of the island and playing with that. So yeah, that's it for that one. Are there any questions on how that part works? Cool. So that kind of brings me to the end of the Unity-isms, which is good because I'm out of time. There's a whole dialogue system. There's more information on this link. And then I had some thoughts on level design, which is to reuse as much as possible. In my opinion, everything should be full of secrets and like little sidebars that people can take. I also believe that level design should be merciless. I struggled with whether I should include this, but I think it's true. I think levels that are easy are not worth playing. I also think on a mean streak that the player should feel like they have some sort of autonomy, but that actually their choices don't really matter. Like they're still going to have to do the same experience because ultimately somebody's playing your game. You want them to go through an emotional experience and you want to control that. So if you give them too much choice, you have no idea what game they're actually playing. That's my very jaded, angry opinion. And fight me. And then Unity for Louie, I wrote this in 2018.2, which really stinks compared to modern versions of Unity because the input system is garbage. 2018.2 is the last version before nested prefabs showed up, and I really wish I had been able to use nested prefabs for this game. And the C# compatibility is also woefully out of date, which all of those reasons are really a bummer. Unity is also just really slow on Windows. The machine I wrote this game on is, like, by all measures, a pretty healthy, powerful machine, but Unity, like the editor application, was just chugging through it, so that was no fun. However, designing with components can be really great. Like I said in the beginning, don't fight it, embrace it, use the component. And I'd recommend it to a friend. I would say I'd do it again, even with all the negatives. It's useful. And here's some links that I thought were super useful and helped me. So there's one about this weird dialogue system. The whole pathfinding thing gets sourced from here. There's this crazy cool scriptable object talk that if you guys haven't seen, you should definitely check it out, just as an aside on like scriptable objects in Unity. I didn't actually use scriptable objects in this way in Louie, but the talk informed how I did the whole property as component thing. And then plug for the Art of Code YouTube channel. It's shader stuff. That's it. That's all I got. So if there are other questions, I'd be happy to talk. If you want to talk later, that's cool too. Yeah, my hope is that something in this presentation was interesting. So that's all I got.
Yeah, it was cool. Inspirational too.
Awesome job, Chris. That's a hell of a presentation. Did somebody happen to record it?
Yep, I'll put the recording up as soon as we're done.
Fantastic. Great. Good stuff.
Cool.
Thanks, Chris.
All right.
Yeah,
Sweet.
awesome job. Thanks again.
Share the Steam link.
It's at the end. It's at the end.
Yeah.
Look, it's on
Plug
the
it.
internet,
There it is.
guys.